Hello students, my name is Shashank Shekhar and we are doing a 45-day crash course for the upcoming JEE exam. And today is our 19th day. So yesterday we started the chapter that is electrochemistry and we have seen what are the main conductance, conductivity and all of those that govern a flow of charge in the given electrolyte. Now today we will see how this electrolyte's voltage or you can say EMF is determined. So for that, we will only consider, so we have seen today one of the electrochemical cell, that is electrolytic cell, which uses electrical energy to carry out non-spontaneous chemical reaction. Now today we will consider the second example of electrochemical cell, which is galvanic cell. So what is the main difference between galvanic cell and electrolytic cell is that electrolytic cell converts electrical into chemical energy, while this galvanic cell converts the energy that is produced during a spontaneous redox reaction into electrical energy. So this point is important here, is that it converts the spontaneous redox reaction, the energy, chemical energy that is released during a spontaneous redox reaction into electrical energy. So, so now we will slowly quantify this electrical energy EMF voltage that is produced during this reaction, and we will see how this partial components help to complete the circuit all over. Now, EMF or cell potential is the voltage that is produced during when this chemical process take place, and the amount of current we get is called determined using this cell. Okay. Now it is determined using this Nernst equation. Sorry, so it is determined using this Nernst equation. So we find the voltage that is produced during this reaction and using Nernst equation. Now let us see this electrochemical cell, which is a galvanic cell that I have put up here, and let us see the components of it. The first of all, here is the electrode, the two electrodes that are present. The left side is called as anode and the right side is called as cathode. Now in this setup, we have taken the Daniell cell, which consists of the zinc and copper. So the Daniell cell is just an example of galvanic cell. So it consists of zinc as the anode and copper as the cathode. Second, we have taken a solution of the same metal. So it can be ZnCl and this can be copper sulfate. Okay, so this can be any salt of zinc. So in this case it is zinc chloride, and in this case it is copper sulfate solution. Now what we have done is that we have put a salt bridge here. So what does this salt bridge does is that, so it helps in maintaining the electrical neutrality. So if you want to understand this process of electrochemical cell or the galvanic cell here, so what happens is that, suppose this is the Zn here and this is the salt of Zn that is present. So here zinc in this electrode is present in the metal form, that is Zn form, and in this solution it is present in the form of an ion, that is Zn plus for ZnCl. Okay, now this ZnCl now changes to Zn, and the Cl minus ion slowly move toward the salt bridge. Okay, so how does it happen is that this Zn releases electron. So now this Zn plus, sorry, takes electron. So it takes electron from this Zn. Okay, the electron is taking here. So here left side, so the oxidation will take place. So oxidation will take place on this side. So Zn plus will release one electron, Zn plus electron. Okay, so it will release electron, and in this part Cu2 plus reduction will take place and it will take one electron to form Cu. Okay, now this is the direction of current that is shown. So opposite will be the direction of electron. So you know it very well from the physics also. So where the direction of current and the direction of electron are the opposite to each other. So this is the direction of electron. The electron is flowing in this direction and current is flowing in that direction. So this Zn, that is the metal that is present here, is releasing electron in the circuit, and it is going through this, and they are going through this copper again and dissolving in this solution to form Cu copper, which will be deposited on this metal. Now as this happens slowly, the amount of Zn plus ion, and here the amount of Cl and all the anions or cations get increased. So to neutralize it, you can say the salt which is present, which help in neutralizing this, say the amount of or the gradient of concentration. Now we will not look into the technicalities of the salt bridge. We will just remember that salt bridge is present here for maintaining the electron neutrality by removing these ions. Okay, so that gradient is maintained, and this galvanic cell goes on working and releasing current. What happens if we remove the salt bridge? Then we will get some current for a short period of time, and it will stop after that because of the amount of ion that will be concentrated or that will be accumulated in this solution plus this solution. Okay, so this is the working of this galvanic cell. Now next we will look at the components of this galvanic cell. So it has two cells, so you have seen cathode here and we have anode. Say we have another reaction in which we have silver and we have copper. So silver is going to this 2Ag and it is Cu2 plus. So why are you multiplying this equation by 2 here? Because we want to maintain the electron neutrality, that is the same number of electrons should be same. But if we take the simple equation, that is this, it will be Ag plus 1 electron will give us Ag. So we will multiply this whole equation by 2 and we will get this equation here. Now similarly for Cu2 plus to 2 plus electron. Now suppose we have another equation like this. Say Zn3 plus is taking 3 electron and going to Zn, and when another example, say Cu is going to Cu2 plus 2 electron. Now if you want to take this overall reaction, what we will do is we will multiply this by 2 and this will by 3, so that the number of electron becomes same on both sides. So the equation becomes 2Zn3 plus 6 electrons plus Zn. 2Zn. Similarly, this equation becomes 3Cu 3Cu2 plus 6 electrons. Okay, so when we add both of these equations, the 6 electrons get cancels, and we get it as the equation as 2Zn 3 plus 3Cu 2Zn plus 3Cu2 plus. So the point I want to make here is that we have to balance this number of electrons so that there maintains electron neutrality. So if we want to represent this whole cell, so this cell representation is very important, but because in exams we do get the cell representation and then we have to find out which will get oxidized and which will get reduced. So this is a shortcut trick I have put here. So you have to just remember this word lone, which means the species that is present on the left side. Okay, so this can be considered both for this diagram that we have seen earlier and for this cell representation also. So on the left side, the thing species we have will go under oxidation. So you can see here very clearly. So if you move in this direction, that Cu is converting into Cu2 plus. So it is releasing 2 electrons, that is getting oxidized and is present on the anode. Okay, so this anode is and present on the left side. So if you see the diagram, you can clearly see that anode is present on the left side and it is negatively charged. So this term you should remember, that is lone. So it is a shortcut term for it. So if you want to remember the reduction, it will be just opposite of it. So if you write for reduction, it will be on the right side. You will take reduction. It will be cathode and it will be positively charged. Okay. So if you remember this left hand term whole wise, you can see what is happening on the right side. So this is the whole cell representation here. So if you want to clarify the cell representation, so this double bar means the salt bridge. So in this case, both of the medium is different. So in some cases, it is possible that we take the same bath and the same salt is salt of both the metal is present in the same bath. So we do not put this salt bridge. So this salt bridge denotes here that both the components or both the salts are present in two different baths. The left side is we have the oxidation part, and the right side we have the reduction part, and it is differentiated by a double bar. Now some of the points that is related to the reduction potential is that So what is reduction potential? So first let me define that. Okay. So say we were seeing some half redox reaction, that is Ag plus is going to, so we have this reaction here, that is Ag plus is going to 2Ag. Okay. So 2Ag plus is going to 2Ag. Similarly, copper is taking 2 electrons, or you can say giving 2 electrons, like this. Okay. So in this case, this is the thing that is getting reduced, and this is the thing that is getting oxidized. Now what is reduction potential is that it is denoted like this. So Cu 2 plus and Cu. Similarly, we have for Ag, that is Ag plus and Ag. So this is the reduction potential. So you can say it is the work done, that is in changing it from Ag plus to Ag. So in simple terms, we want to remember it. So for the half cell, we have different E cell. This is the thing. So we are seeing that Ag plus is going to Ag. That is, it is getting reduced. So it is the reduction potential. So whatever value will be given, it's called as reduction potential. So say it is X volt. And similarly, since Cu2 plus is getting to Cu, it will be the reduction potential of Cu2 plus, that is Y volt. Now the point I want to make here is that the first point says that if X is the reduction potential, then minus X is the oxidation potential. Now if you want to represent the oxidation potential, so it will be written like this: Ag will go to Ag plus. So you can see here clearly that Ag is going to Ag plus. That means if Ag is going to Ag plus, that means it is releasing one electron. Okay. So it should be very clear. So it is the oxidation potential. So our reduction potential was X volt. So oxidation potential will be minus X volt. Similarly, if we want to write the oxidation potential of Cu, which will be represented like this, then it will be minus Y volt. So you should remember this thing, that oxidation potential and reduction potential are nothing but with the negative sign of each other. So they are the opposite sign of each other. Now the cell having a greater reduction potential will get reduced, and vice versa is for oxidation potential. So here what I mean is that suppose you are given two species whose reduction potential are like this. Say we are going from A to A plus, and its reduction potential is given as X, and we are going from B to B plus, then its reduction potential is given Y. Now if X is greater than Y, it means that this will get reduced because its reduction potential is greater, and which will get oxidized. So this one will get oxidized. So for this case, oxidation of A takes place and reduction of B takes place. Now this is the case. Now we have, suppose we have galvanic cell which consists of A and B, and you are set to calculate the EMF of this. So how you will calculate is that you will take simply the summation of both this thing. Now the thing that you have to make the difference is that so since this is going under reduction, so you will keep its sign same, but since this is going to oxidation, so it is undergoing oxidation, so this is the reduction potential, so you need the oxidation potential here. So what you will do is simply you will convert. So I have told you earlier that if you just reverse the sign of it, you will get the oxidation potential. So while we are calculating the EMF of a cell, the thing that is getting reduced, we should take its reduction potential, and the thing that is getting oxidized, we should take its oxidation potential. And in case reduction potential is not mentioned or oxidation potential not mentioned, then we will simply reverse the sign and add it. So if you want the EMF of this cell that is consisting of A and B, such that the reduction potential of A is greater than the reduction potential of B, then how will find it? So you will take the summation of reduction potential of A, that is X, and oxidation potential of B, that is minus Y. So the EMF of that cell will be this, X minus Y volt. So this is a very clear illustration. So in NCRT we do have a different formula, but I'm just giving a broader sense that you can easily solve for it without any confusion. Okay, so this is the thing for the finding of EMF directly. Now one more thing that should be kept in mind is that EMF of a cell is never an additive property. So we will see this thing in the later slide also. Now this is the Nernst equation we have. So I have told you earlier that if you have to quantify this electrochemical cell or the galvanic cell, then you need this Nernst equation. Likewise, we need that Faraday equation for quantifying the electrolytic cell. So what is this Nernst equation? It says that EMF of any cell is equals to E naught minus RT by NF ln Q. So what is this E naught here? This E naught here represents the EMF of the cell at standard conditions. So what I am saying is that if you take the standard condition, that is suppose it is said that okay, that the pressure is 1 atm, the temperature is kept at 25 degrees Celsius, and all standard condition are taken, then the EMF that is measured at that condition is called the standard EMF. So the first thing to notice here is that E is the you can say the difference of E naught minus RT by NF ln Q. So those who are not knowing about this value here, so it is given as RT by F is equals to 0.059. So temperature, if it's mentioned is the temperature mentioned is 25 degrees Celsius, then only you will take this. You can say this value. So if it's different, you have to take all the values and multiply it and get the final value of RT by F. And if it is mentioned that the temperature is 25 degrees Celsius, then you will simply take it as 0.059. Okay. And the value of this Faraday is 96500. Okay. Now next, so what happens at equilibrium is that this delta E becomes 0, and this whole equation can be further written as E naught is equals to RT by NF ln K. So you know very well that at equilibrium Q is equals to K. So I have just replaced it and written K. So these are the two forms of Nernst equation. So you will be using it to and fro. Now we have this very idea of Gibbs free energy. So we have to introduce to a new formula, that is delta G is equals to minus NFE. And in standard condition it will be delta G naught is equals to minus NFE naught. So if you have not derived the Nernst formula, then let me give a quick you can say derivation of it. So we know it very well that delta G is equals to delta G naught plus RT ln Q. Now if you put all the values here that is given, minus NFE and minus NFE naught, you will get the final Nernst equation. So this Nernst equation is nothing but derived from this relation. Okay. Now let us move to how to measure this reduction potential. So we measure this reduction potential using a standard hydrogen electrode. So we'll see what it is in the later on slide. So we have put an image also. So the key point is here is that if we see at the electrochemical series, so what is electrochemical series? So it is basically a series which consists of the reduction potential of all of those elements that we know, and we take hydrogen as the standard one whose value is 0. So if we are going from H plus to H2, suppose we have an equation here which is H plus going to half H2. So we'll take one electron here. Okay, so we'll take one electron here, or either this equation or either this equation, both equations. Half H2, H plus, then one electron. Okay, in both this condition, the EMF, the delta E naught that will be found, it will be E naught that will be found, it will be equals to 0. Okay, but E naught, the thing in has to mention is that E naught value is 0. Why? It is taken at standard condition only. Okay. Now next, species having unknown reduction potential is kept on the right side. So when we see the diagram, we will see that on left side of this means the oxidation side, we keep this hydrogen electrode, sorry, the platinum electrode, and we put up some gas here. So you will see in the diagram later on. Okay, so on the right side we will keep this thing whose reduction potential is to be determined. Now one having the greater reduction potential, so this are key points related to reduction potential. So if something is having a greater reduction potential, it will be a better oxidizing agent. So you must have studied this concept in redox also. So I'm just making a glimpse of it. While one with the smaller oxidation potential is a better reducing agent. Okay, sorry, here will be greater word. Greater. Okay. Now next, let us see the type of electrochemical cells we have that we use daily. So if you want to define, so if you want to means bifurcate, we have two types of cells, that is primary cell and secondary cell. So what is primary cell as that we use in our battery and all. So it is a non-rechargeable battery and has a generally lower capacity but a longer shelf life. So the common example are lithium batteries, alkaline batteries. Now on the second half, we have the secondary batteries which are rechargeable. So these are the batteries like we have in our the inverters. So that are rechargeable batteries. They have a higher capacity. So you know very well that they can be, you can say, they can supply power to a greater area, or you can say to greater applying voltages area, and it has a shorter shelf life. Now it is the common example are lithium ion batteries, so it is a very greater interest for the research scientists and all. Now let us see how does this work. So I put up here an example of a mercury cell. So this one is used in the watches. So the first thing to notice here is that at anode we have this mercury amalgam, which is going under oxidation. Similarly, we have a mercury oxide which is going reduction. So this is the thing, this is the working of this mercury cell which is used in the batteries of watches. So this is the anode part, this is the cathode part, and we have the separator which separates both of them, and this is just a cascade to protect this overlayering. Similarly, we have example of here of a dry cell. So it has a cathode that is made up of carbon rod. Then we have zinc cup. So zinc is here. So zinc is here the thing that is getting oxidized. And MnO2 plus carbon base black plus NH4Cl. So the MnO2 species is getting reduced here. Okay, so these are the two primary batteries that we use in our daily life. Now this is the example of an inverter battery. So it is a very complicated, it has a very complicated mechanism. So we'll just look at the anode and cathode reaction. So this is the anode that is present, the cathode that is present. So in anode, we have this PbSO42 minus, Pb is getting oxidized and PbO2 is getting reduced. and we get over all this. So if you add this both equations, that will be so at the anode and the cathode, then you will get the overall reaction. So this is an example of a secondary battery, so it is rechargeable. Now this is the in eco-friendly cell that is called as fuel cell. So this has been working on work has been going on this on a greater extent. So basically we are using just water and oxygen, so that both are present in the environment and in bulk amount, because you know that 70% of our earth is consisting of water. So we are just using that water to convert it into energy. So it is a very, you can say, phenomenal work that is going on. So this is the you can say a schematic diagram of that fuel cell, of one of a fuel cell schematic diagram. So from left side we have this anode. Similarly on the right side we have this cathode here. An aqueous electrolyte is put here. So it is consisting of water. Now what the reaction is taking place is that from left side we get inside the hydrogen, and it is getting reduced to this. You can see here the equation. So hydrogen is getting from this side, and we see here that it is getting oxidized. Similarly, we have oxygen on this side and it is getting oxidized. Now overall reaction is this. So I am giving you this example so that you can know that what a numerous application of this electrochemistry is in the daily life. Okay, so and why some questions are asked on this place only. So these are the example of the cells that we have discussed. Okay, now let us see what is corrosion. So if you want to describe corrosion in brief, so it is not about iron only. So many of the metals do react with oxygen and gets corroded, or you can say they get into powder form. In simple terms, they get into powder form. So copper also get corrodes. This iron also get corrode. So for the term that is used for iron corrosion is called as rusting. Okay, so the rusting term is used for iron corrosion, and this is the anode reaction that takes place, and this is the cathode reaction. So suppose this is the representation of moisture or the water droplet. Now what happens is that this Fe iron metal present here, it get oxidized by converting into Fe2 plus and releases 2 electrons in its metal surface. Similarly, one more Fe is getting oxidized to Fe2 plus, releasing 2 electrons. Now the 2 electrons that is produced during this oxidation of iron metal is used by the water to get reduced. So water is present as H plus and H2O. So H plus and O2 minus. Okay. Now this H plus here is taking electron that is released by this Fe. So it is taking this electron, and we get here 2H2O plus the oxidized form of water of iron, which is Fe2O3. So this is the representation of rust that is formed. Okay, so this is an overall representation of corrosion. So if you look at the anode reaction, you can see very clearly that two of the iron atoms are getting oxidized and releasing 4 electrons, which has a potential of 0.44 volt, minus 0.44 volt. Sorry to not mention here the value of this thing. I don't know the very clear value. I'm just representing the cell here. Okay. Now if you add both these equations, you will get this equation finally. So this electron will get cancelled. You know very well, because you have to maintain the electron neutrality. So this is the very idea of corrosion. Now we have seen a numerous application of this you can say electrochemistry in various parts of our life. Now let us move to some of the questions that we have here. So in an electrolytic cell, flow of electron is from where to where? So I have put the image of that electrochemical cell, or so galvanic cell. So if you have seen it, so electron was moving from left to right. Okay, so electron was moving from left to right, and on left side we have the anode. So it is happening from anode to cathode. Okay, through internal supply. Okay, Now next, the standard reduction potential for Fe2 plus to Fe is and Sn2 plus to Sn is given respectively for the cell reaction what is Fe2 plus and SnFe2 plus. Now one thing I want to make clear here is that suppose we have reaction A which has a cell potential of E0 and a reaction B which has a cell potential of E10. Now if you are said that okay, calculate the cell potential of this reaction that is A plus B, then you will not simply add this two. Why? Because the very you can say crucial part of this EMF is that you cannot add it because it is an intensive property. So you have what you have to do is first you have to calculate the delta G or the Gibbs free energy, which is an extensive property as it depends on the number of moles, and then you have to find the delta G for this A plus B, and the value which you will get, you will further use it to find the E naught again. So if you want to solve this question, you can do it like this. So it is you can use this also, but it is done in wrong way. Why? Because you can see here that we are simply adding this two, but you cannot add this two. But the answer that you will get is similar to this delta G calculation. Why? Because both are involving two electrons. So you can see here the number of electron is same, and during the calculation all these things will get cancelled. Now how we are doing is this, that we know that this thing here Fe2 plus has a reduction potential of 0.44. So here you can see that it is getting reduced. Okay, so you will not convert this value, keep it as same. But Sn is getting to Sn2 plus. So you cannot just add this value simply because it is getting oxidized. So how we will get the oxidation potential? We will just reverse the sign, that is minus to plus, that is plus 0.14. Then we will add and get the EMF of the cell, which is this. Okay, so this is the answer for it. Now let us consider the next question. So we have here is that three species that are X, Y and Z whose reduction potential is given 0.52, minus 3.03 and minus 1.18. And what we have to see the reducing power. So which one is getting easily reduced, which has a greater reducing power. So I have said you earlier that the thing that is getting reduced easily has a smaller reducing power or a greater oxidation power. Now we have to find the opposite order. So let us see how can we solve it. So x has a given value of 0.52, y is 3.03 and z is minus 1.18. These are all the values of the reduction potential. Now this x has a greater reduction potential, so it will have the smallest reducing power. So x will be at the least. Now out of this two, z has a greater reduction potential, so it will have a this place, and similarly y. So this is the order of the reduction potential, and opposite is their order of this reducing power. Okay, so y will be greater than z than x. So if you see the solution here, so greater the reduction potential, less is the reducing power. Okay, now the decreasing order of reducing potential is this, then this will be your final answer. Okay, so in this way you can solve this. Now next, what will be the EMF of the given cell, that is this. Now here we can see very clearly that we are representing not the H plus ion but the pressure. So do not get confused, because if you see the formula of this, it was given as RT by NF ln K. It was not mentioned anywhere that K should be equal to Kc. K can be also equals to Kp. So we can use the pressure term also. Now how we will do this? We have to find the EMF of the cell. So if you have to find it at standard condition, sorry, if there is a negative sign here, then this E will be 0. So E naught will be equals to RT by NF. What is present on the, so if you write the equations for it, so H2 is going to H plus. Okay. Similarly, H plus is going to H2. So here one electron is taken and here one electron is released, and half H2. Okay, or you can write it in the either way also if you want. So two electrons here and two electrons here. So what is the number of electrons that is involved? So n will be equals to 2, and H plus H2, this H2 which has a pressure of P1 is on the left side, and H2 which has a pressure of P2 is on the right side. So the Kp is written as this, that is pressure of P2 which is P2 divided by P1. So we'll take the ln of it, and n will be equals to 2. Okay, so this is the correct answer. If you see the solution, okay, the correct answer here. Now next, the standard EMF of a cell involving one electron is found to be this. The equilibrium constant is what? So the standard EMF given, that is E naught value is given, and we know the relation between the K equivalent and E naught. So it is given at E naught is equals to 2.303 RT by NF log K equilibrium. So we've put this value of E naught cell. So upon putting this value, so if you solve it further, then it will be 0.591 by 0.0591 is equals to log K equilibrium key. So with this will be a 10. So K equilibrium will be 10 to the power 10. Okay. Now next. So now upon I will not solve this question. I will just give you a direction how to solve it, and you solve it by yourself. So what does this question say is that we have an E naught of Fe3 plus, which is 0.036, and E naught of Fe2 plus, reduction potential of Fe2 plus. So both are the reduction potential because Fe3 plus is going to Fe, which is the reduction, getting 2 electrons. Similarly, Fe2 plus is going to Fe, which is also reduction potential. The value of the standard electrode potential for the charge is given by what? So we have the two equations here, which is Fe3 plus is taking 3 electrons and going to Fe, and Fe2 plus is going taking 2 electrons and going to Fe. And what final equation we need is that Fe3 plus should be on the left side. So this should be on the left side. Okay, so this equation will keep as it is. But we need Fe2 plus on the right side. And the number of mole is same, that is 1 mole of Fe3 plus and 1 mole of Fe2 plus. But we need to reverse this equation. So what we will initially do is that we'll find the delta G. Why? Because we have told it earlier that you cannot add it simply because E naught is not a additive property. So first you will calculate delta G for both of this reaction. So first you will reverse this because you need this on opposite side. And then you will calculate delta G for both of this. So you know the formula very well, that delta G is equals to minus NFE. Now since you are reversing this second equation here, the E value should also be get reversed, so it will be positive 0.439. Then you will calculate delta G for both of this using this N. Now whatever value you will get delta G, you will equate it with the equation which is delta G is equals to minus NFE. Now note here that for this reaction the number of electron that is involved, it is 1. So we will put N value as 1, then F, then E you will find because you know the delta G value from the previous calculation. So in this way you can find the answer of it. Now next question we have here is Zn2 plus, Zn is going to Zn2 plus and Fe2 plus is going to Fe. The EMF of the cell is also given. It is 0.295. We have to find the equilibrium constant. That is K. Okay. So we know the Nernst equation. minus RT by NF ln K ln Q. So we have to find at equilibrium. So this equation will become E naught is equals to RT by NF ln K. Okay. Now the thing I have to mention here is that we do not have this, say we do not have this value of E naught here. Okay. And we have the value of EMF. Okay, so we do have the value of this thing. So what you will do simply is that for this equation you will first write the equation very properly. So it will be go from Zn to Zn2 plus, that is 2 electron, and Fe2 plus Fe. So 2 electrons are involved here, so this n value will be 2. Now you will simply put the value of all of this and get your K. Okay, so you will do it by yourself. Now next question we have is that the cell is given, that is Zn2 plus to Cu2 plus to Cu. The E naught cell value is given, and we have to find this ratio, that is Zn2 plus by Cu2 plus. So similarly you will write all the equations. So first of all you must write the equation that is involved in it, so that you can get the number of electrons and all of those values. So the similar equation will be formed here also. So if you write the whole equation, it will be E cell is equals to E naught cell minus RT by NF ln. So what is the product? That is Zn2 plus by Cu2 plus. Now E naught cell value is given, that is 1.10. Also the concentration of Zn2 plus and Cu2, so it is not important. Okay. So we'll put all these values, so E will be equals to 0, and then you will find this value. Okay. Now next. So here is an example of rusting of iron that we have here. The rusting of iron takes place as follows. So its value is given this. Similarly, we have another equation that Fe2 plus is taking 2 electrons and its E naught value is given. So what we have to calculate is the del G naught value. So how I will calculate it? So first we will reverse this equation. Why? You know it very well, because we know we need the oxidation potential, because Fe must be going to Fe2 plus, because in rusting process Fe is going to Fe2 plus. So we'll reverse this equation. It will be plus 0.44 plus 1.23. Then you add both of this, and we know the formula that delta G naught is equals to minus NFE. We'll put all the you can say values. That is value of electron will be 2, F will be 96500, and the addition of both of this will be E naught. Then you can get your delta G. Now next, this is the last question we have here. So given data at 25 degrees Celsius, this is the value. So Ag plus ion, we got it as this, and this thing. So what is the value of KSP? So those who do not know what is KSP, it is simply the concentration of Ag plus into concentration of I minus. Now the E naught value is given here. So if you write the K for this equation, so for both of this, that will be Ag plus, okay, that will be Ag plus and AgI. So we will use this equation KSP is equals to Ag plus into I minus. Then we'll put the value of E naught, we have it here. So we know that it is given K. So K is at equilibrium constant. So E will becomes equals to 0. We will put